Swayam Prabha. Digital India. Educated India.
All right. So, good morning, good afternoon. Welcome back to our course on analysis and design of rigid pavements. In this course, we are currently in module 3, which is the analysis of rigid pavements using the finite element method. Just a reminder for where we are in this course. So, module 1, it was an introduction. We looked at different types of rigid pavements. In particular, we looked at one type of rigid pavement, JPCP, jointed plain concrete pavements, which are by far the most common type of rigid pavements. So all our discussion analysis was basically for JPCP. There is another type, CRCP, continuously reinforced concrete pavements. To a large extent, its analysis tends to follow JPCP. So although I'm not talking about CRCP, and it is also not very commonly used, but it's not unknown, unheard of, or very rare either. So although the discussion mostly is talking about JPCP, understand that CRCP is following very closely along. Most of the tools which we learn can also be used for CRCP. Now, module 2 of this course was on analysis of rigid pavements using classical methods. I had defined that classical methods basically mean old methods. They are methods where a differential equation was solved using analytical solutions. So the analytical solutions then have a particular solution which, under a set of assumptions, the solutions are exact. There is no error in the solutions. Of course, the assumptions might be wrong or right, but under those assumptions, if those assumptions are true, then the solution is exact. It's actually called analytical or classical methods because they don't require a computer to solve, or at least you don't need a very sophisticated computer program to solve them. The mathematics is fairly straightforward. You can solve it by hand if you wish. You could use a calculator. You could use a spreadsheet program. Relatively simple to solve, relatively simple to calculate. The problem, as we started seeing with those methods, is they make many assumptions to get those analytical solutions, which are not actually reasonable assumptions. Perhaps the biggest and most unreasonable assumption is that the slabs are very large. That is, the distance from the load to the joints is very large, such that the joints are not having a significant effect on the stresses at the point where the load is applied. As we saw in some of the previous lectures, that's actually quite a pretty bad assumption. And then for more reasonably sized slab, we can end up overestimating stresses by as much as 50%. So that's twice. We can end up overestimating the stresses by 50% or even more if we go for such an approach. Another problem with these analytical solutions is that we have to make assumptions about the tire footprint. So Westergaard solutions, which is the most celebrated of the analytical solutions, Westergaard solutions actually assumed a tire footprint which are circular. Some simplifications and some assumptions were made later in subsequent solutions, not by Westergaard, but by other authors, where you could have a square footprint. But that's basically it. As we saw in a previous lecture, the realistic footprint of a tire is very complicated. It has a very odd and irregular shape. It actually follows the shape of the treads of the tire. Furthermore, the stress distribution of the tire is also non-linear. And so it is quite difficult to actually be able to use Westergaard's theory to actually accurately analyze a load as a realistic load. There were other shortcomings as well. The Westergaard theory or the classical theories, they allowed for tension swings. That is, when the plate is pushing against the ground, then the plate is pushing back, that's fine. But when the plate is moving upwards and it is not pushing against the ground, then the ground is pulling the plate back down, which is obviously unreasonable. And if you step foot on the ground, you know that's not how the ground actually behaves. So these and several other limitations we saw were shortcomings in Westergaard's theory and the analytical solutions. And while these in their day, in about 100 years ago, these were okay to try to at least scientifically analyze and design rigid pavements, over time it was found that these are leading to such gross assumptions and such gross oversimplifications that they were not working very well anymore. The way out of this solution actually appeared around 30 years ago, that is using the finite element method. So the finite element method is a mathematical technique. It's basically used to solve differential equations. It's a mathematical technique where, first of all, we assume that we are not going to get an accurate solution. So in analytical solutions, as I pointed out, if as long as our assumptions are correct, we will get an accurate solution. There is no error involved in our calculations. In the finite element method, the first thing we do is we give up on the idea that we can get an accurate solution. We are okay with an approximate solution. And I would like you to go back to about 2 lectures. I had a discussion there on why, as engineers, we are actually okay with accurate solutions. It's okay with less than accurate solutions, with solutions with some approximations. It's because there's so much uncertainty in construction that eventually any solution which we believe is accurate is not perfectly going to show what is happening in reality, because the reality itself has a lot of variability involved. So for that reason, again, go back to that lecture to see that discussion. But we are okay as engineers to have some amount of approximation in our solutions. Okay, so that's one assumption we made, that in the finite element method, we give up on the idea that we're going to have an accurate solution. We are going to be okay with, say, 1 to 5% error as compared to the true solution if we had a true solution. The other assumption we make in the finite element method is that we are no longer going to solve our displacements, our stresses, or more broadly, our degrees of freedom. We are not going to solve them at an infinite number of points. We first of all take our domain, we take our geometry, and we discretize it into a series of finite points. We are only going to solve our equation, our differential equation, at those points. And the values that we solve at those points, I had called last time as degrees of freedom, TOFs. So now, instead of trying to solve, let's say, for displacement or stresses everywhere in the slab, we are actually only going to solve the displacements or stresses at those particular nodes. And so we call them, the displacements in particular at those nodes, we call them degrees of freedom. Nodes themselves, they have a finite number of nodes. So at each node, we are going to calculate our unknowns, our degrees of freedom. And then we assume that each node is connected, a set of nodes is connected into a finite set of elements, hence the name finite element method. But we assume that nodes are grouped or collected into elements, and there are a finite set of elements. Within each element, we assume that the solution varies using some simple polynomial. So it could be a linear polynomial, it could be quadratic, you can have various schemes. But we assume that within each element, we have some simple polynomial approximation for the degrees of freedom. So the degrees of freedom are known at the nodes of the element, and within each element, we assume that we have some polynomial approximation. Now, with all of this, in the last lecture, we started the process of developing a finite element method for plates. In that, we particularly looked at a particular formulation called the MCZ element. In today's lecture, what we're going to do is, we are going to complete that discussion. We are going to formally derive the stiffness matrix and the force vector of the MCZ element. As a reminder, in the finite element method, we start with a differential equation. We end with a series of algebraic equations. And it's not going to be a small number of algebraic equations. Practically, it will be millions of algebraic equations. We end up with a large number of algebraic equations, which you can write compactly as Ku is equal to F, where K is called the stiffness matrix. So let me write it down. So K is called the stiffness matrix. The stiffness matrix contains all the physics. So it is a discretized form of all the physics of the problem. F is a vector which generally we call it the source vector. But in some applications, particularly in structural engineering, we may also call it the force vector. So the source or force vector contains all the information about the external load which is being applied. And this U is the vector of the degrees of freedom, is what we're trying to solve. So ultimately, in the finite element method, we are going from some differential equation or even a system of differential equations into a very large system of algebraic equations of the form Ku is equal to F, which then we give it to a computer to solve, because solving millions of equations is not something you want to do by hand. So in today's lecture, we will see formally for the MCZ element, how do we derive the stiffness matrix and the force vector? And then we will go on to define something called local support and global system of equations. So I'll explain what local support and global system of equations is, and we'll see how it is not just useful, but it's actually the linchpin. It's the main reason why the finite element method is so useful and so efficiently implementable on a computer. Okay. But first, as I said, in the finite element method, we are basically solving a differential equation. So let's go back and recall what differential equation are we solving for rigid pavements. Recall, this was the Sophie-Germain equation. So this is the equation of a plate where we assume that the plate, when we assume this is a medium thick plate, so medium thick plate, for a medium thick plate, we have this particular equation and we assume here that W represents the displacement along the neutral plane. So we are only solving this along the neutral plane with the additional assumption that shear strains are not admissible. So if I have a displacement above the neutral plane, vertically above the neutral plane, I'll have the same displacement vertically below, and this whole line, which is perpendicular to the neutral plane, I'm going to have the same displacement throughout. So I am not going to have any shear strain or any transverse strain. Based on those assumptions, and a second assumption which we make for JPCP is that the slab is sitting on a subgrade. And the subgrade itself is modeled using what we call a Winkler foundation, sometimes also called a dense liquid foundation. So it's basically a bed of springs. The springs then have some spring coefficient K. And so when the plate is deforming by W, a reaction force is going to come from the springs, and that reaction force is going to be equal to Kw. So we just add it as an additional force. So the Sophie-Germain equation is just the first term, and on the left hand side and the term on the right hand side, we add this additional term to account for the fact that we also have these Winkler springs. Where W is a function of only X and Y, no transverse shear is allowed. So our displacements are not a function of Z, they're only a function of X and Y. D, by the way, I had defined previously. D is EH cubed divided by 12 into 1 minus mu squared, where E is the elastic modulus, H is the thickness. So all the information about the thickness of the plate is actually contained inside D. Mu is the Poisson ratio. This D is what we had called the plate stiffness. So, and we also saw last time that this equation is a fourth order biharmonic equation because you have this del bar 4 term over here. Also recall now last time what we said is, so this was the equation that Westergaard actually solved. Westergaard gave us analytical solutions and then subsequent authors gave other analytical solutions. Coming to the finite element method, we actually saw the derivation of an MCZ plate. So an MCZ plate is a 4-noded plate. Each node consists of 3 degrees of freedom. The degrees of freedom are W, which is the displacement at the node, and it also contains the first derivatives of those degrees of freedom. So del W over del X and del W over del Y. We interpret these physically as being rotations. So one way of putting this is that in an MCZ element, we have 4 nodes. Each node has 3 degrees of freedom. The degrees of freedom are the displacements and the rotations about each axis. But mathematically, the mathematically accurate way to put it is the displacement as well as the derivative, the first derivatives of the displacements of the system. So each node has 3 degrees of freedom, which we can compactly write into this vector W bar. Again, this underbar I'm using as a vector. This is W1, theta x1, theta y1. That's the degrees of freedom at node 1. So this is node 1. Degrees of freedom at node 2, theta W2, theta x2, theta y2. At node 3, it's going to be W3, theta x3, theta y3. And at node 4, it's going to be W4, theta x4, theta y4. So total, we have 12 degrees of freedom. So we can write this compactly in the form of this vector W, which is a size 12 by 1. Now, what we had started on last time was, of course, this rectangle can take any shape you want. We started on last time that let's assume this rectangle is of size A by B, that is along the x-axis, and let me just draw the axis over here. So this is x and this is y. Along the x-axis, it has a length of A. Along the y-axis, it has a width of B. So we just start with this. It's not a bad assumption to make. It's general enough that we can solve most problems using this assumption by just plugging some values of A and B. So for that, we saw that the first thing we need to do is we have our degrees of freedom, 12 degrees of freedom at the nodes. We need to be able to interpolate. We have our degrees of freedom at the nodes. We need a set of interpolation functions that allows us to calculate the displacement at any point inside the element. So again, we only know the degrees of freedom at the nodes inside the element, we are going to have to interpolate between the elements. So between the degrees of freedom. And so we had to come up with some interpolation function. I pointed out that those interpolation functions, which are allowing you to interpolate not just a value, but also its derivatives, are called Hermite interpolants. And it's actually not a unique set of interpolants. We have a choice of variety of interpolants that we can use. And what we saw is that these three gentlemen, M, C, and Z, go back to my previous lecture for their names. It's Malosh, Cheng, and Zenkowitz. But if you go back to the previous lecture, you'll see that we actually derived from a basic assumption they made. So they made a basic assumption of what the polynomial form of the displacement looks like. And from there, they went on to derive these shape functions. So these shape functions we got over here. Note, this is also a 12 by 1 vector. So we have 12 shape functions, we have 12 degrees of freedom, and we have 12 shape functions. So each shape function corresponds to each degree of freedom. So for example, the first shape function corresponds to W1. The fourth shape function corresponds to W2. Similarly, we've got W4. Similarly, we've got W3. Similarly, we've got W4. The second shape function corresponds to theta x1. The third one corresponds to theta y1, and so on. So each unknown or each degree of freedom has one shape function, and we successfully derived this shape function. Please review the previous lecture if you forgot how we derived this. I'm going to start with the assumption that we know these shape functions. You will also note that the shape functions, each of the shape functions was fourth order. That's going to be useful because as we look forward towards the end of the last lecture, what we left on was this discrete strain operator. So what we don't care too much about, the degree of freedoms are fine. What we're actually interested in is stresses, and before stresses, we're interested in strains. So it's fine if we can express the displacements using this using degrees of freedom and using an interpolation. We would actually like an interpolation that gives us the strains. That's how we start off with our analysis. So we had derived, when we did plate theory, we had derived three equations. We had derived that epsilon x is equal to minus z del square w over del x square. Epsilon y is equal to minus z del square w over del y square. And epsilon xy is equal to minus z del square w del x del y. Please go back to that lecture on plate theory if you forgot how these are derived. I don't want to repeat it right now. And what we do is, in each case now we have the w is n transpose bar w bar. So we have a discretized form of w. We can plug it into these three equations. And then we finally get that epsilon, the vector, which is a vector which consists of these three components. Epsilon, which is a vector, is minus z, b, w bar, where b is a matrix and it's going to be a matrix of size 3 by 12. Each column of b is going to correspond to each degree of freedom, and each row of b is going to correspond to the component of the strain, that's epsilon x, epsilon y, or epsilon z. So what you can see clearly over here is this b, which again we call the discrete strain operator. It's a very important term. It's important that you know what it is and you are able to define it clearly. B is the discrete strain operator. So the discrete strain operator, for example, now consists of del square n transpose del x square, del square n transpose del y square, and del square n transpose del x del y. We had n previously in these slides. So what I went ahead and did is I just evaluated these derivatives and I wanted to show you what b looks like. Again, b is of size 3 by 12, so I couldn't fit it into one slide. So I'm just showing it in two slices. So first of all, I'm showing, so if I have a 3 by 12, I'm just cutting it vertically like this. So I'm showing you first of all a 3 by 6 matrix, which is this part, and then I'll show you the next part, 3 by 6 in the next slide. So here is what the 3 by 6 matrix looks like. What you will obviously see is that the highest order of the polynomial is 2. So we have a quadratic term over here. So the highest order of each of these polynomials is actually 2. That is to be expected because n, as we showed previously, was basically a fourth order polynomial, right? We saw that it's in these slides. N is a fourth order polynomial. So each interpolating polynomial is fourth order. So obviously, if b is going to take the second derivative of n, then it's going to turn into a second order polynomial. So exactly as we expect, this is how you check whether the calculation is correct. Although I did this using Mathematica, it's almost certainly the calculation is correct. But again, you should know how to check whether it's correct. So you'll see that each of these interpolating functions is a second order interpolator. Furthermore, what you'll see is that you have this, in each element, you actually have zeros. So when you're trying to calculate epsilon x and epsilon y, it turns out that some polynomials are not going to contribute to it, whereas both polynomials will end up contributing when you have epsilon. You try to calculate epsilon xy, what this third row is talking about. So this was this first half of the matrix, this 3 by 6. I want to show you the next half of the matrix, which is again a 3 by 6 matrix. This is what it looks like. So this is basically column 1 through 6, and now I'm showing you column 7 through 12. Similar idea over here. You'll notice each of these is a quadratic expression. That's exactly what we expect. And as we see here, for epsilon x, the middle value is becoming 0. Similarly, for epsilon y, the last value is becoming 0. For epsilon xy, no such thing is happening. So that gives you an idea what is the structure of this B matrix. Now, given the structure of the B matrix then, so the ultimate thing we'll talk about is, so we know what the B matrix is, right? We won't go into a lot of details on doing the calculations, but we know what it is. So now we can fully express epsilon as minus z B into W bar, where B is some known matrix. It's a function of x comma y for the element which is an A by B element. Also notice that you have a minus z over here. That's correct. We know that the bending strains are going to be a function of depth. In fact, they vary linearly with depth. So if this is the neutral plane, we know that the bending strains are going to be varying linearly, and bending stresses similarly vary linearly. So the fact that we have a minus z over here is correct. Again, this minus z is basically with respect to the neutral plane. So z is pointing downwards over here. All right. So those are some preliminaries. So now we have two important operators that we defined. We defined n. N was our interpolating operator. We defined it. And b, which was our operator for strains. We defined this also. So a discrete strain operator, this was our interpolation operator. We are going to use these two operators to formally derive the finite element formulation, which is to say that for this one MCZ element, we are going to derive what is the stiffness matrix. Again, we start from the differential equation. So d del power 4w plus kw is equal to minus q. If you go back to my previous lecture where we did a simple toy example about 2 lectures ago, I had said that first of all, what we do is we write the residual of this differential equation. So the residual is defined as left-hand side minus right-hand side. So the residual is going to be d into del power 4w plus kw plus q. If w is exact, that if somehow we have calculated the exact analytical solution, then it's going to be equal to 0. But in general, w is not going to be equal to 0. We are calculating an approximate solution, so we're going to get an approximate answer. So our residual will not be 0. In the finite element method, we use a particular method called the weighted residual technique, WRT, where we assume that, okay, the residual is not 0, but the weighted residual throughout the whole domain is 0. In other words, if we take the residual R, we multiply it by some V. V is some weight function. And we integrate it over the entire domain. So I'm going to integrate over dA. We would like this term to be 0. So our error is not 0, or our residual is not 0. But the weighted residual error, the weighted error or the weighted residual throughout the whole domain is 0. That is what we would like in the finite element method. So now if I substitute R into the equation, then this is my weighted residual formulation. V into the whole thing into d lambda power del power 4w plus kw plus q integrated with respect to A, which is the area, is equal to 0. Now, what we talked about last time is we also have to check the continuity requirements for these approximations. What we see over here is that we have a fourth order derivative on w. That means for w, a fourth order derivative must be defined. Another way of writing that is w must be C4. It must be fourth order continuous. Generally, what we see in the finite element method is when we have such high continuity requirements, we can start having trouble getting an analytical solution. Our order, we end up having to have a very large number of elements in order to get an accurate solution. Instead, what we would like to do is we would somehow, as we saw in the previous example, we would somehow like to reduce the order of this derivative. We do not want a fourth order derivative. We would like to be able to reduce it. How can we do that? Well, if you just take a look at this term, we actually have a v del power 4 w integral of this. So v has no continuity requirement. So the continuity requirements on v, the test function or the weight function, is actually 0 because we don't have to take its derivative. Whereas the continuity requirements on w is c4. That's pretty heavy. It would be nice if we could split them halfway. That is, it would be nice if somehow we could insist that we have a C2 continuity requirement. So we are increasing the continuity requirement on V, but we are decreasing the continuity requirement on W also to C2. So that now equally both are balancing out the burden of approximating this fourth order derivative. In the previous lecture, when I had just solved the toy part differential equation, I had shown you that the way to do that, the way to basically move this derivative from one term to another term around is using integration by parts. Integration by parts. Again, this I hope and I assume all of you learned integration by parts in high school. You might want to just go back and review it if you're a little bit confused at this point. But integration by parts is a method that basically we use it. Well, mathematically, there are a variety of reasons we use it, but the basic property of integration by parts is it's going to shift the derivative from one term to another term, which is exactly what we want. We have a fourth order derivative on W. We want to shift it around and put the fourth order derivative, a second order derivative on V and a second order derivative on W. Now, it so happens that integration by parts is actually something you do in one dimensions. So all of you, I'm sure, studied integration by parts. It's defined for a one-dimensional term. When you do integration by parts in higher dimensions, then there's a more generalized version of it, which is called Green's theorem. It's not important for us to know Green's theorem. Again, this is not a mathematics class. It's not a class on calculus. Green's theorem, I'm assuming you would have studied in your first year engineering mathematics course. If not, it's perfectly fine. You can just look it up on Wikipedia or Google it. It's not particularly difficult and it's not important to know all the details. Just know that Green's theorem is sort of an analog of integration by parts in higher dimensions. Okay, so what we're going to do now is, now that we have this weighted residual form, we are going to apply Green's theorem on this form, and we're going to divide this fourth order derivative equally at a second order and second order among V and W. Over here, what we have is we have a W into V. There's no derivative over there, so there's nothing to divide. Here we have a Q. Q is again a known value. That's our external load. So we have a Q into V. There's no derivative again. There's nothing to split up, nothing to divide. So we only have to apply Green's theorem on this first term in order to ease up the continuity requirements. Instead of having a C4 requirement, we will now, instead of having a C0 requirement on V and a C4 requirement on W, we just going to have a C2 requirement on V and W using integration by parts. Okay, so we perform some sort of integration by parts. We're going to convert our C4 requirements into a C2 requirement. So I'm not going to go into a lot of details. Again, I assume most of your civil engineering students, and therefore, well, even if you're not, you should really take a formal course in finite element methods so you'll be able to understand how this formally works. So I'm not going to go into a lot of details, but our original equation was basically the integral d is just a scalar, so I can move it around, dv del power 4w plus kvw dA is equal to the integral of q, so I want a minus q, minus vq into dA. This, when I apply Green's theorem and I move the fourth order terms around, I basically end up getting this. So I get a del square V and I get a del square W. This double dot, for most of you, this might be the first time you're seeing, this is basically called a tensor contraction. So it is sort of like a dot product, but dot product is applied on vectors, and this double dot is a more general way of doing it on tensors in general. So it's not particularly important for you to understand how this comes and what is the meaning of this. I do recommend you should take a class formally in finite element methods where you learn these details, but it's not that important for now. So basically what you see here is we have a del square V and an inner product with del square W. The del square V, so V now has a C2 requirement and W also has a C2 requirement. So we have successfully reduced our continuity requirements on W from C4 to C2. In that process, we have raised our continuity requirements on V from C0 to C2, which is fine. The other terms, VW, there's no issue. Both of them can be C0. And VQ, Q is anyway a prescribed constant, and V is just V. So there's nothing to do over here. Now what we do is, so this is our basic differential equation. This is our differential equation in weighted residual form, where we have used Green's theorem to reduce the continuity requirements. Now what we do is, now we apply our finite element approximation. Our finite element approximation, first of all, we assume that W is equal to N transpose of W, N transpose bar, W bar, because W is constant, but N transpose bar and W bar are vectors. And then one of the assumptions, which again, if you go back 2 lectures ago, one of the additional assumptions I said is we assume that this test function V, which is a weight function, this is going to have the same functional form as W. Or putting a little more mathematically, it belongs to the same space as W. So we write this as V is equal to V transpose, which is some matrix or some vector of constants, into N. Now, when we substitute these in, one additional thing we'll notice is del power 4 of N, del square of N is B. I would like you to go back and check that yourself. So I had this formulation for B over here. You will see del square is, you're basically going to get these 3 terms in del square. So del square of N is basically, so del square of N is basically going to give us B. Okay. So what we have here then is, we have this D into del square V, del square W. So we're actually going to get a D, B, B transpose. Why? Because we have N. So when we're taking del square V, we are actually getting del square V bar transpose, V bar is a constant, into N bar. Since this is a constant, we can take it out. Del square N is simply going to be B. So we get D, B, B transpose. We get K, N, N transpose. This whole thing is actually going to be multiplied with V transpose. Similarly, on the right-hand side, the whole thing is actually going to be multiplied by V transpose. We can just cancel V transpose out. We do end up with a W bar on the left-hand side that's coming from this approximation for W. The right-hand side doesn't have a W. So both the left-hand side and the right-hand side have a V, and therefore the V bar is getting cancelled out. But only the left-hand side has a W. So we cannot cancel out W. So we get this formulation as the integral of D into BB transpose plus K into NN transpose dA into W. W is an unknown vector. And the right-hand side is the integral of minus N Q N bar, I should add here, minus N bar Q into dA, which is, again, N is a known set of polynomials, so we can perform the integration. So we know everything about the right-hand side. Q is prescribed, N is known. On the left-hand side, we know B, we know N, we know K, we know D. So we can evaluate this matrix. Therefore, we call this, formally, this is our definition of the stiffness matrix for this 4-noded 12 DOF MCZ element. It is the integral, this is an area integral, by the way. This is an area integral within that element, B, B, B transpose plus K, N, N transpose. And we can also define the force vector, or sometimes this can also be called the source vector, same thing. So the force vector is negative integral within the area N, Q, dA. Note I'm putting the superscript E in this case. This superscript E stands for element. This is the stiffness matrix and the force vector for the element. Sometimes we also call this as the local stiffness matrix and the local force vector. Local in the sense it's only for that element. We will see what the opposite of local, which is global, we'll see what that means. So the FEM formulation for this particular element becomes KE for this element. U or WE, you can use either notation. So KE, WE is equal to FE. So if our JPCP slab, again, we're just doing an approximation of the slab. If our JPCP slab consisted of one element, then we have successfully taken our original differential equation, the Sophie-Germain equation, and we have reduced it to a system of 12 algebraic equations, which we can then further solve in order to get the degrees of freedom at the nodes. That is basically the fundamental idea of the finite element method. So previously, we had the Sophie-Germain equation, and we, or rather Westergaard and those before us, they came up with these analytical solutions. What we have done is we have come up with an approximate solution where instead of solving a differential equation, we are actually converting it into a system of 12 algebraic equations, and we're simply going to solve those equations. Now, as I said, this element or local stiffness matrix is 12 by 12. So always it's going to be size of degrees of freedom by degrees of freedom. That's also something to keep in mind. The size of the stiffness matrix is going to be, it's always going to be a square matrix. It's going to be of size degrees of freedom by degrees of freedom. And the element or the local force vector is going to be of size 12 by 1. Again, this is a vector. So it's going to be always be of size DOFs by 12. Now, obviously, if I ask you to solve, it's very easy to say I can calculate these. Sure, I can perform the integration and I can calculate them and I can invert it. But something that all of you would rightly complain about is that's pretty mathematically demanding. First of all, to be able to integrate a 12 by 12 matrix, that we're basically asking you to integrate 144 expressions, and similarly integrate the right-hand side. So you're asked to evaluate an additional 12 expressions, and then to invert a 12 by 12 matrix, or to solve a system of 12 differential equations, 12 algebraic equations. It's a lot to ask to do by hand. Fortunately, computers are actually very good at it. So at this point, you may be asking, in previous modules, whenever I went through a lot of mathematical formulation, I have always done a solved example. Why am I not doing a solved example? Because we do not do solved examples by hand in the finite element method. Truly, for a practical application, such as the one we're doing here, there is no point doing it by hand. For small toy problems, maybe, but not for this application. So take my word for it now that we will have a computer program that can do these calculations for us. I'm not going to show the details of the calculations for now. In practical applications, we always use some computer application, but as engineers, it's important for us to understand where those equations, where those formulations come from. How is the computer solving the problem? Do not use the computer as a black box, but don't try to replicate what the computer is doing either, because it takes too much mathematical effort. Anyway, so the short of it is we've derived a system of 12 linear equations. We can solve them. We'll let a computer solve them. We'll look at such a solution a couple of lectures from now. So now we have a solution. Now, keep in mind, as I said, in the finite element method, the first assumption we make is that we do not have an accurate solution. We are not even interested in getting an accurate solution. Our solution always has some error. And so what we are actually interested in is, what is that error? What is the accuracy of our solution, and how can we get a more accurate solution using the finite element method? Okay. So what we have currently is, suppose we approximated our JPCP slab using that one plate with 4 nodes. So we've got 4 nodes and 1 plate. We can definitely place a load anywhere on it. We'll see such an example a couple of lectures from now. We can calculate displacements. We can calculate stresses. The main problem is, if you recall 2 lectures, the error in the finite element method, it goes to 0 only as the number of elements goes to infinity. And you will agree with me that 1 and infinity are not even reasonably close to each other. So 1 element is definitely not a lot of elements. So the problem here is, we have seen how to solve this system for 1 element. But when we have 1 element, we should not even expect a very low error. In fact, we should expect a very high error when we have just 1 element. So although we have derived the entire formulation for this MCZ element for a single element, actually what we need to get a reasonably accurate solution. By reasonably accurate, I mean our error is, say, within 1% or 5%. In order to get a reasonably accurate solution, we don't need to solve for 1 element. We actually have to discretize our slab into many more elements. So for example, we might have to do this. So suppose I have a rectangular slab. The dimensions are not important. Obviously, I've exaggerated the size a little bit over here. But suppose we have that element, which is a rectangular slab like this. Let's say in this case, previously I was discretizing it into 4 nodes. Now let's say I choose to discretize it into 6 nodes. So I've got here node 1, node 2, node 3, and then, node 1, node 2, node 3, node 4, and then I have 2 more nodes, node 5 and node 6. Another way to look at it is, this was my slab. Originally, I was putting nodes only at the corners. Now, along these 2 edges, also I put some nodes. I can put nodes wherever I want. So I additionally added these. So now what I have is, I actually have, if I consider this whole thing to be 1 element, that I have taken my slab and I have discretized it into an element that consists of 6 nodes. 6 nodes and therefore 18 degrees of freedom. So this is what you could think of this as, a 6-noded element with 18 degrees of freedom. As it turns out, that's not the way we want to think about it. But we can start with that assumption. Okay, so what did we do for the 4-noded 12 DOF element? We had to come up with an interpolating polynomial. That interpolating polynomial had to have 12 terms. We had to do quite a bit of sophisticated algebra, including inverting a 12 by 12 matrix, in order to get the interpolation functions. We could do the same thing here. In this case, we have 18 degrees of freedom. we could try to find some 18th order polynomial to approximate W. And then we will end up having to invert an 18 by 18 matrix. I think you can clearly see that if 12 by 12 was hard, 18 by 18 is pretty hard. And furthermore, these are just two elements. In general, as I said, we don't solve just a handful of equations or a handful of elements. We go into millions of elements. Are we going to derive an interpolation function? Are we going to derive a new interpolation function every time we decide to add more nodes? And are we going to really try to invert an interpolation function which has a million terms in it? It's completely impractical to do it this way. So in the finite element method, we actually have two options. When we are trying to have more than just one element, when we're trying to increase the number of nodes in our system, we have two options. We can come up with an entirely new interpolation scheme. So as I said here, we have an 18 degree of freedom system. We can try to come up with a W, which is some 18th order polynomial, and then go through the entire process of the MCZ formulation. It is quite hard to do mathematically. It's also quite useless with further refinement, because if I started with 6 nodes, what stops me from adding 2 more nodes, for example, over here? Nothing stops me. And so I might have 18 degrees of freedom. I can immediately go to another 24 degrees of freedom. So no matter how many degrees of freedom you have, I can always give you more degrees of freedom. So it's not a generalizable approach. I guess that's the point I'm getting at. So instead, in the finite element method, we actually use a completely different approach. That different approach is generally, the technical name for it is called local support. But what it basically means is we make the following assumption. The degrees of freedom are only connected to other degrees of freedom in the same element. So for example, let's go back to this. So if you notice here, I've got node 1. Node 1 consists of degrees of freedom 1, 2 and 3. And let's say I've got node 6 over here. Node 6 consists of degrees of freedom 16, 17 and 18. Now, in real life, these nodes are just points on the slab. So in real life, if I applied a displacement to node 1, if I pushed that node down, I would expect node 6 to respond. I would expect some displacement to also occur on node 6. The assumption we make in the finite element method, it's an assumption. The assumption we make is that that is not the case. Node 1 and node 6, node 1 belongs to element 1, node 6 belongs to element 2. They are not, we assume that they are not connected to each other. That is, if we add a displacement to node 1, then it does not directly affect node 6. It's an assumption which is made. This assumption is what we call local support. That is, if we have a degree of freedom, then the degree of freedom, if we move the degree of freedom, or if we apply any change to the degree of freedom, it is going to change the degrees of freedom of the same element, but not the degree of freedom of other elements. That is a very, very important assumption that we make. In other words, we say that the degree of freedom is locally supported. It is affected by other degrees of freedom within the same element, which we call locally affected. It is not affected by degrees of freedom in other elements. So this assumption which we make is called local support. As it turns out, this assumption, and again, I emphasize the fact it's an assumption. This is not what happens in real life. In real life, if you applied a displacement at node 1, you are going to get a displacement at node 6 if this was an actual plate. So this is a mathematical assumption we're making. But as it turns out, this assumption is the linchpin of how we are going to use the finite element method to solve for JPCB slabs and indeed to solve for any kind of structure. The assumption is here as follows. Previously, we know that for each of these elements, so I've got 2 elements here, element 1 and element 2. Element 1 consists of nodes 1, 2, 3 and 4. And degrees of freedom 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So totally, I know that my local stiffness matrix KE is 12 by 12. That's exactly what I derived earlier in today's lecture. Okay. So the assumption of local support is as follows. My global system, this entire system of 6 nodes consists of 18 degrees of freedom. So let me expand my local stiffness matrix KE into a global stiffness matrix. The KE is 12 by 12, but KG, the global stiffness matrix, is 18 by 18. So what I have here is I have written out sort of schematically, this is an 18 by 18 matrix, which is a global stiffness matrix. Now, within this, we know that the degrees of freedom 12, the first 12 degrees of freedom, so this degrees of freedom 1 through 12, both the columns and the rows, the first 12 degrees of freedom we know are connected to each other, which means that my KE for the first element, which I'll write as KE1, is actually contained inside this. And then we made the assumption, which is the assumption of local support. We said we are making an assumption that any degrees of freedom which are not connected within the same element are not connected to each other. So, for example, degree of freedom 18 is not connected to any of the degrees of freedom in KE1, because this degree of freedom 18 up here is not part of element 1. Another way of writing that is the stiffness matrix, which connects degree of freedom 18 with element 1 is basically zeros. That is, there is no connection between. So my global stiffness matrix, accounting for only element 1, basically consists of a large number of zeros. So it's just a very large, it's a matrix of size 18 by 18, full of zeros, except for this 12 by 12 block over here. That corresponds to degree of freedom 1 through 12 rows as well as columns. So I have this 12 by 12 block that contains KE1, and the rest of the global stiffness matrix is 0, because there is no connection for element 1. The connections of element 1 are only between the nodes of element 1, and the nodes or degrees of freedom of element 2 are not directly connected to it. Now, that is for element 1. What about element 2? If you look at this diagram here, which I have element 2. So, element 2 consists of node 2, node 5, node 6, and node 3. So, it consists of DOFs 4, 5, 6, 13, 14, 15, 16, 17, 18, 7, 8, 9. So, obviously, for this element 2, I can always write KE2. I can write a local stiffness matrix, which is of size 12 by 12. But now, if I want to express it in global form, that is, I want to write it in terms of an 18 by 18 stiffness matrix, then that stiffness matrix is mostly going to be 0, except for the degrees of freedom which are connected by the element 2. So, element 2 has degrees of freedom 4, 5, 6, 7, 8, 9. It has degrees of freedom 13, 14, 15, 16, 17, 18. So what we do here is we actually end up cutting up our KE2, our local stiffness matrix for element 2. We will end up cutting it up and putting it into these little boxes over here, surrounded by a sea of 0. So all of these other values around this are 0. So in KG1, we had one local area where all our element 1 information was present, and element 2 has no connection with element 1. So the degrees of freedom in element 2 don't have any connection with degrees of freedom in element 1, and therefore the rest of this global stiffness matrix was just 0. Similarly, in this case, it's not quite as neat. It's not one little nice block over there, but it's still generally the same idea that we've taken this KE2 and we've just put it in this global stiffness matrix. We've put it in the corresponding locations, that is the corresponding degrees of freedom, and then everything else is 0. So in element 2, degrees of freedom 4 and 4 to 6 are connected, and therefore you have this little block. Degrees of freedom 7 to 9 are connected. But in element 2, for example, if I go back to element 2, in element 2, degree of freedom, for example, 13, 14, 15 is not connected to degree of freedom 1, 2, and 3, because 1, 2, and 3 is not part of the element 2. And therefore, the corresponding rows and columns, so the rows, so if I look, this one, if I look at 10, 11, 12, and 1, 2, and 3, that's basically this block over here. This has no connection, therefore it's going to be 0. And therefore, you have a lot of zeros and non-zero values only where some amount of connection exists. This, again, I emphasize, this is an assumption of local support. Why do we make this assumption? Because if we assume that element 1 and element 2 are of the same size, and that the material properties, that's E, H, and nu, they are the same for them, then we actually have KE1 is equal to KE2. The two elements are identical. They are just connecting different degrees of freedom. So we only have to derive one local stiffness matrix. We use it twice. So the advantage of this particular approach is we don't have to go back and derive a brand new stiffness matrix and therefore interpolation functions every time we add more nodes and add more elements. We have one 4-noded element with 12 degrees of freedom. We have the stiffness matrix for that. That's all we have. and we can then reuse it and continue to use it for any other case that we would be interested in. We can do the same thing, by the way, for the force vectors. So FG1, so this is the global force vector, but only those components which are coming from element 1. Element 1 consists of degrees of freedom 1 through 12. So what we have is FE1, which we know how to calculate that. FE1 is simply going to come in this block, and the remaining values are going to be 0 because of the assumption of local support. Similarly, for FG2, again, 4, 5, 6, 7, 8, 9, and then 13 through 18, those are the degrees of freedom which are present in element 2. So those values will be there in FG2. So this is basically going to come from FE2. But the other values are going to be 0 because there's no connection between them. And so now what we have is, we have a KG1, which is of size 18 by 18. This is the global stiffness matrix. It is the stiffness matrix of the global 18 degree of freedom system, but only those components or those contributions from element 1. We have KG2, which is also 18 by 18. Again, it's a global stiffness matrix, but with only those components which are contributing from element 2. Similarly, we have FG1 and FG2, which are 18 by 1 each. Similarly, they only have the contribution from element 1 and element 2. We can then define the global stiffness matrix of the entire system is simply the superposition of these individual global stiffness matrices, which is to say Kg is equal to Kg1 plus Kg2. Both are 18 by 18, so this summation is valid. Similarly, Fg is equal to Fg1 plus Fg2, both are 18 by 1. So this is how we get the global system of equations. So we are actually going to solve Kg Ug, so is equal to Fg, where Kg is an 18 by 18 global stiffness matrix. Recall that Ke we had called a local stiffness matrix. This is the global stiffness matrix. The local stiffness matrix is always going to be 12 by 12 no matter what. The global stiffness matrix depends on the number of degrees of freedom. Similarly, Ug is the global vector of degrees of freedom, and Fg is the global force vector. The local force vector Fe will always be 12 by 1. Fg, in this case, it's 18 by 1. As I show in the next slide, it can be whatever size our system is. So this approach of using local support to assemble this process, what we just talked about, of adding these vectors and these matrices together, this is called assembling. So this process in the finite element method, where we assume local support, that's the big assumption. We assume local support and we assemble a global stiffness matrix from local stiffness matrices. And the local stiffness matrix we derive from our fundamental formulation, where we do weighted residual, etc. This is the basic reason why the finite element method is so useful, because you only have to derive the local stiffness matrix once, and the rest of it is just algebra. It's just defining a stiffness matrix, adding certain rows and columns of matrices or vectors. Computers are very good at doing that. So if we can take care of the physics of defining the local stiffness matrix and the local force vector, which is the MCZ element in this case, the rest of it can easily be implemented on a computer. It actually takes no more than maybe 10 or 12 lines of code. Can we extend this further? Absolutely. So here I have a system where I actually took our plate, our slab, and I discretized into 9 nodes. And each of those 9 nodes have now been collected into 4 elements. So our elements 1, 2, 3, 4. So now I have a 9-noded system. Each node has 3 degrees of freedom. So I have a 27 degree of freedom system. If I had to go back to the beginning and derive a 27th order polynomial, it would have just basically been impossible to do it. But in this case, what I have is, I have a local stiffness matrix, which is 12 by 12 for each of these elements. And then I just have to assemble them into a global stiffness matrix, which is of size 27 by 27, just by looking at which degree of freedom is connected within each element. So it's a very easy and convenient way to do it. We're not going to do the computer programming it of this class. Again, I strongly recommend, if you want to know more details of this process, take a course on finite element methods. It's a very interesting and fascinating topic. We can't go through all the details in this class, but we can develop a global stiffness method, a global stiffness matrix accordingly. So regardless of whether we have 27 degrees of freedom or we have a million degrees of freedom, we just need a 12 by 12 local stiffness matrix, 12 by 1 local force vector, and the rest of it can be done very straightforward way using a computer. Of course, now keep in mind, this approach does have some shortcomings. There is some loss of accuracy. with respect to analytical solution. So no matter how many elements we have, until we get to infinite elements, which in practice we can't do, if we have a finite number of elements, we are going to have a finite error. But as we already said, this is fine. We can live with this. We are okay if we have a small amount of error, as long as we don't have to solve complicated differential equations for which solutions are very difficult to find. The other downside or the other disadvantage of this approach is, as I've been pointing out, it's mathematically quite tedious. Again, you may want to go back to the original lectures where we started in module 2, where we looked at Westergaard theory, Freiberg's equation, etc. You might be a little bit nostalgic because those were so easy. Those were some simple equations where you could plug in values, and I showed you how to plug in the values. Mostly you had to be careful of units, that was it. In this case, we had to do quite a lot of heavy-duty mathematics over here just to get to this point. But again, I emphasize, a computer can implement. So we do not do any of this by hand. I'm teaching you how to do it so that you are aware how it's done, but we don't do this by hand. Okay, so that was a extremely brief and quick introduction to the finite element method as it applies for JPCP pavements. Now, as you recall, when we started Westergaard's theory, we looked at Westergaard's theory, we looked at the modifications, that was for an individual slab. Then we took some time to study joints, and we looked into Freiberg's equations and the analysis of dowels in joints, and we also looked at load transfer. Well, naturally, our FEM analysis is going to follow a similar progression. Now that we've seen how we can use the finite element method to analyze an individual slab, in the next 2 lectures, we are actually going to see how to use the finite element method to analyze joints in between the slabs. And here you will see something remarkable about the finite element methods of mixing different types of elements and still being able to solve the system. So we will continue on joints in the next lecture. Thank you.